Hi, this is Akshaya Rajakumar. So this is the video demonstration for lab 7 of EE533. Our teammates, team members are Siddarth Sadeesh Kumar, Akshaya Rajkumar, and Shreyas Jaikumar. So now I'll be proceeding with the GPU data path. Um, so this is the data path for the GPU. And most of it is similar to the CPU, except for the register files and the processing elements, um, and the data mem as well. So for the register file, we have used a 64-bit wide register file, so that for each vector has like 4 packed elements. So each data width is 16 bits. So we have like 4 of that in one single register file. So if one address points to a data, it has like 64 uh, 64 bits, and 16 bits are given to one processing element. The other 16 is given to another processing element. So like they will be computed in parallel. So I'll show you the SIMD core here. So as you can see, the most of the signals are similar to that of the CPU. So here I've instantiated the register file, and then when we come here, uh, we have this. So in this, I'm extracting the parts of the data which is supposed to be given to the processing element. So the first 16 bits is named as R1 data lane 0. So this is going to lane 0's processing element, and this is R2 data lane 0. So similarly, I'm giving I'm extracting out the bits, 16 bits of the next next lane. So these are the 4 lanes that we are using here. And when I come down here, so here, uh, as we can see, so this is similar to the ALU, where the processing element is similar to the ALU, where the second input will be selecting depending on the register destination. So we're doing that. Mm. And here I have instantiated 4 processing elements which can read, which can take in data in parallel and compute. Here I'm giving instantiating 4. Let me show the processing element. So the processing element is also like similar to the ALU, but then we have an input called lane. So this is basically we'll have this mask, which is also known as the predicate. So basically, if we want to mask one of the processing element while computing the data in parallel, so we can just disable that lane. So in order to do that, we'll have this lane number and mask. So if the mask is like 4 bits here, so it's like representing each lane. So if the second bit is 0 for the mask, then lane 2 has to be deactivated. So that is why I've implemented that here. So as you can see, here I'm giving, here I've defined it as mask. Whatever, like we're masking it, that will not be, that will not be performing the operation. It will basically retain the previous data. The out will retain the previous data. So here we have like 2 16-bit inputs and one 16-bit output. So for multiplication operation, um, what happens is we are giving two B float 16 data types, and that will get multiplied. Like that will first be converted to FP32, and then it will get multiplied, and then the result is again going to be converted to B float 16. So that is why we'll have like 16-bit output only. Mm. So we also have a ReLU function inside the processing element, and this is to compute flags. And when we come here, yeah, we have the opcode and also the functions that are to be selected. So for the multiplication, so there can be two types. One can be integer multiplication and one can be BF16 multiplication. So I've implemented it here. So for now, I'm taking like if the data type is mm, like bfloat16, that is going to give this bfloat16 result, or else it will just give like normal integer result. So that I've implemented here. So as you can see here, I have like three models for this. One is two models for this. One is bfloat multiplication and another is bfloat addition or subtraction. So addition and subtraction I've implemented in the same module, and bfloat16 multiplication I've done it in a different module. I'll show the bfloat multiplication here. As you can see, uh, so this is in accordance to the like the paper by Google. So we've taken references from that, and we have uh, done this. So this does the normalization, rounding, all that, and then finally it converts the output to bfloat16, takes in two bfloat16 values, then conversion, all of that is done in a single module. And also here, this is the bfloat16 add sub module. So if do sub is 1, it does subtraction, or else it does addition. So, and the output is also bfloat16. So this is also similar to the normalization, rounding process, all of that is similar to the multiplication as well. So it's same. And this is the addition. Mm, so I have like I've done this like here, like I've sorry, yeah, here I've implemented this here, and then yeah, depending on the opcode, depending on the data type in the instruction, it will be either bfloat or integer. And here in the assembly code, yeah, we have this like after the data comes out from all of these. So I've we have like a single memory of with the 64 bits. So yeah, we are storing first 16 bits from the processing element 0, next 16 from processing element 1, and so on, like 4. So yeah, I've declared a single wire which is 64 bits, and then writing parts of it from different processing elements. And all of this is similar to the pipeline CPU. So yeah, here we have the DMEM data, like this is also similar, like uh, yeah. Yeah, and we have the write back data as well. Like basically we just duplicating the ALU like into 4 parts, and then even the memory and the register files, and then we are computing everything in parallel. And for the control unit also, based on the ISA, the PTX translation, we will be dividing the instruction split will be based on the PTX ISA, like the PTX. So we have developed an ISA which is like compatible. We have also a translator. Uh, which converts the PTX into an ISA, where we can generate control signals based on that. Yeah, and this is the whole of GPU. And now the tensor unit will be discussed by Siddarth.
Hi, so I will explain about the tensor core unit. The tensor core unit is our main critical unit for a GPU, mainly in what our plans are with the GPU. We are planning on doing AI processing, in which you need like multiple matrix multiplication and addition. So for that, we're going to use matrix mac, which is basically essentially a tensor code. We can also use tensor code more towards an hardware accelerated point of view. So in that also you need to do a lot of mac applications to like find vector dot products in which you're going to use a tensor core. Our application more towards the AI processing, which is basically not going to have being. It's going to be basically like Mac application, which is like so. For this, we are doing to more towards a B float 16 based tensor unit. So for that, if we multiply two B float 16, we get a B float 32. So we are adding with a C, which is like the addition part, which is also going to be a B float 16. So I'll show you how we designed our Mac. So basically, there's two approaches to designing a Mac. One is using a systolic because the main critical issue with the matrix application is getting the inputs. So like you're gonna get an array of inputs and you're gonna have to arrange it in a matrix and then load in the do matrix multiplication with that. You can't do like straight up do anything else other than that. So we have two approaches. We either get a systolic array based input and then like structure it and do Mac application based upon that. Using that, we can get a more of a dot product, which is not ideal for an AI application point of view. It's more towards an AI accelerators, hardware accelerators point of view. So we try to figure out, we try to do something similar to that, and it wasn't working out pretty much. But like we took the core elements of this and designed our final unit. So the core elements of it is around our Mac. So this is our Mac unit. So it's going to be multiplication and accumulation. So this is actually for our multiplication part of view, and then accumulate the end product at the end. So for that, this is our Mac. So there's like a single bit input and then, or like, I think single bit, right? Yeah. No, this is a 16 bit and 31 bit input. Just multiply that and keep it aside. Then as we have an input of array of input coming on, we're going to add with every multiplication is going to get added at the end. And then that's our final product, which is more towards an dot product for which is like, as I said, for an accelerator. So instead, we are going to like use some elements of this and make our final project. So which is here. So wait, I'll show you the other one. So this. So finally, we came across this. This is like our basic skeleton, which upon which we just further modulated it. So we thought of going with either like a Brockram side kind of thing instead of matrix. So in that essence, it will be like this, almost like this, and we just like, I mean, this is a bare metal like skeleton, and based upon this, we're just gonna uh advance it further and further down, scale it down. So this is like kind of like what the idea we are approaching for it, and we did this kind of skeleton, and then further we just like thought of just going with getting the data as an array, and then like put it in a matrix kind of shape. So which is again what we ended up like finally going with, which is like get the data as an array stream, and then get just load it in our um, array matrix a register, which is like a matrix. So that, and then yeah, this is our ABC, which is like C for accumulation, A and B will be multiplied and D will be output. So this is like we're writing it into the array. So this is the logic for the array. So A by 4, sorry, this is like okay, this is right pointers for us A and B and C. So basically, when it's right enable, the pointer will be constantly increasing, and based upon that, will be like it will start from I comma j. So I comma j. So I comma j is going to increment, and then we're going to have from it's going to start from I don't know I some 1, and then j will just be more 1, 2, 3, 4. Similarly, I will increase to 2, and then let's increase 1, 2, 3, 4 like that. Basically, based upon that, we're going to like store the whatever getting data stream into the matrix. After we get in the matrix, kind of simpler to do further. So for this again, we are having and for loop for multiplication for matrix multiplication. So that with every I and j incrementing, we're just going to multiply it. So again, it's all based upon our first initial idea, just building on further and further apart. For it, we're able to like end up in this kind of structure, wherein I and j will just increment, and then you're gonna multiply and add, multiply and add, multiply and add. So yeah, that's our main tensor core plan for tensor core, so, and which have been implemented and got some successful results.
Yeah, sorry for the inconvenience caused. So basically, these are the output files after having executed the PTX underscore GPU translator. So as I said, right, so the first file is the assembly file. So based on the 32-bit split that we have given, those 32 bits, the corresponding hex are being mapped into 32 bits binary, and then the respective instruction is being generated, as you can see over here. So this is then very helpful for us when we have to test out our GPU's data path design, so that we can actually verify that the instruction correctly matches with the hex and etc. So yeah, so this is what we have given in our output executable. Just going to slowly scroll down it. These are all the comments that we had given out in the start. So basically how the instruction split should be for all the three different types of instructions. For R, I, B and T, the opcode table which is present in part of the code itself, the branch label, so basically what the different basic blocks are and how many types the loop unrolling happens, which this I talked about in the PTX instruction itself, the actual register allocator table, and this is the key part of section 4, which is where the allocation, when the allocation and the eviction process happens. The actual COE file which will be fed into the instruction memory whilst implementing the block RAM generator from Xilinx ISC. Sorry for that stuttering in the last part. And the hex, so basically it's the same, that's in COE format because that could be like directly fed into the instruction memory. So yeah, so this is like a detailed video on the first part of the deliverable, and now I would like to hand it over to my teammates, wherein they will start to talk about the GPU's data path, the implementation, the implementation, the design process, and etc. Thank you so much.